There are 2 trillion galaxies in the observable universe. You need to know that the Milky Way galaxy has got 200 billion stars. Most of those stars, we now know, have planetary systems. We estimate there are something like 20 billion Earth-like planets, or potentially Earth-like planets, in the Milky Way galaxy alone. So if you're asking questions about what is my place in the universe, you need to know those things first of all. It's a framework within which you can think. I've been doing some work on black holes, and there's progress being made on that now, which I think is profound and exciting. These are stars at the end of their life, bigger than the sun, more massive than the sun, but they run out of their fuel and start to collapse because gravity squashes them. If they're sufficiently massive, then there's nothing that can stop the collapse. So they collapse, as far as we know, to a point, essentially an infinitely dense point. They collapse to such an extent that there's a region around them from which light can't escape. So nothing can escape. That's a black hole. They're surrounded by this region. If you fall into it, it's called the event horizon. Once you go across that horizon, you're going to the center. There's one way of thinking about it which is quite cool. Time and space sort of flip. In the same way that we're going to the future now, going tomorrow, and there's nothing we can do about it. In the same way, if you fall and across the event horizon of a black hole, you're going to the middle, the singularity, it's called. That's your future. Every line of your future points to the center of the black hole. We have now got photographs of them, radio telescope photographs. One of the black hole in the center of our galaxy, which is a small one, is called Sagittarius A star. It's about 6 million times the mass of the sun. They also took a photo of one in the galaxy M87, 55 million light years away. That black hole is around 6 billion times the mass of the sun. If you took our sun, you can fit 1 million Earths inside it, and collapse it down, it would form a black hole when it shrunk. You'd have to squash it down until it's about 2 miles in diameter, and then that would form a black hole. 6 billion times the mass of the sun means multiplying that mass by 6 billion. These things, the so-called Schwarzschild radius, is larger than our solar system. What you're seeing there is the emission from the material swirling around it. It's called the accretion disk. You have material that's orbiting very fast, emitting a lot of radiation, and that's what you see. It's a flat disk, by the way. Think Saturn's rings. The material is very flat. But in that photograph, you're seeing the light rays being bent around the black hole from that flat disk. That was a prediction from Einstein's theory, published in 1915. You could predict what one should look like. Then, about 4 or 5 years ago, for the first time in history, we got an image of one, and it looks like the prediction. In space science at the moment, we have this debate a lot. Space probes like Curiosity on Mars are really cheap compared to sending people to Mars. So, often scientists who want to find out about other worlds will say, we should spend on robots, not people. But I think crude space exploration is important. Clearly, humans can do more than robots right now. We can explore better. It's about living and working off the planet, which is quite a persuasive argument. We've already industrialized near-Earth orbit. It's already a multi-billion-dollar industry. Communication satellites, whether satellites, GPS, we're already up there. So, learning to live and work in space is a natural extension of our civilization. Plus, if you talk to Elon Musk or Jeff Bezos, they point out that the amount of resources available just above our heads is vast. I remember talking to Jeff Bezos once. He thinks really simply, and he said, for example, in the asteroid belt, there's enough metal to build a skyscraper 800 stories tall and cover the Earth in it. Not that we want to do that, but his point was that energy from the sun and the resources are all up there. You could imagine zoning the Earth as residential in the future, to protect the planet and do your heavy industry off Earth. It might sound like science fiction, except that now SpaceX and Blue Origin have reusable rockets. So suddenly, the economics become sensible. I think expansion is good, and I think we will expand. We will expand outwards because there's not much room left on this planet. That's a different idea. It's not about gathering scientific information. It's about the frontier and the benefits that come from operating as a civilization on a frontier, which we've lost on Earth. There is no other planet we can go to other than Mars. You can't go to Jupiter or Saturn. You can't go to Mercury or Venus. If we want to go somewhere and expand our civilization, it has to be Mars. And everything's there that you need. We now know quite a lot about the history of Mars. It's clear that there was water, almost certainly oceans and rivers. That water is almost certainly still there. There's definitely ice, and there may even be pockets of liquid water below the surface. Couple that with the minerals and resources we know are there, and you have everything you need. That's the thing about Mars. It's quite nice, relatively speaking. You can't go to Venus, just melt. It's 400-something degrees Celsius and has 90 times Earth's atmospheric pressure. Even in our own solar system, I wouldn't be surprised if we find microbes on Mars, or on some moons of Jupiter or Saturn, where there's liquid water. Why do I think that? Because if you look at the history of life on Earth formed, there was no life, just a ball of rock. But almost as soon as it cooled down, we see evidence of life. Certainly 3.8 billion years ago, possibly even further back. So somewhere along the line, geochemistry became biochemistry on Earth. We have some idea that if you get temperature gradients, acid and alkaline conditions, and the right chemistry on the surface of oceans, complex carbon chemistry happens spontaneously. We know that life probably began on Earth. The other option is it came from space, but probably not. It probably began here. And we know the same conditions that led to the origin of life on Earth were present on Mars 3.8 to 4 billion years ago, and they're present on Europa, a moon of Jupiter, today. So I don't think there's anything special. Life is just chemistry. The idea that geochemistry becomes biochemistry is not fanciful, because it happened here. Given the same conditions, it would surprise me if the same thing didn't happen elsewhere. To test, that is one of the great frontiers of science. That's one reason we're interested in Mars. We know those conditions were there. We know there were hydrothermal vent systems on the floors of ancient Martian oceans 3.8 or 4 billion years ago. So it would be good to know whether what I'm saying is right. The way we find out is to find life, or evidence of past life. There's a theory called the Grand TACK theory. It's hard to explain the evolution of our solar system. When you do computer models of solar systems, you don't usually get 4 rocky planets close to the sun and 4 big gas giants farther out. One of the current best theories suggests that Jupiter formed and migrated inward, almost to where Mars orbits today.